In this segment, we'll look at floating point instructions in ARM. Floating point computations are considerably harder than integer computations. Operations must deal both with the mantissa and the exponent, and when you're doing addition and subtraction, you have to do some major bit shifting to line up both operands at their corresponding binary points. Also, most modern processors perform more complex operations as well, like powers and roots, logarithms, trig functions, all in hardware. The hardware to do this is called a floating point unit, or FPU. A decade or two it would have resided on a separate chip, nearly as complex as the CPU itself. In modern processors, it's part of the CPU die, but still a separate unit that interoperates with the CPU, as we're showing here. For this reason, ARM assembly has special instructions for floating point operations and a set of floating point registers, or FP registers, specifically for such operations. The FP registers are actually in the FPU, and the floating point operations are performed by the FPU under direction from the CPU. Just for interest's sake, here's an image of a typical floating point processor. As you can see, it's not a trivial bit of hardware there, quite a lot going on. There are 16 floating point registers, part of the FPU, as we said, and expanded out here. They're designated D0 through D15. These are 64-bit registers, so they hold double precision values. Each register can also be divided into two 32-bit single precision registers labeled S0 through S1. I've shown just two of them here for D0. D0 is also S0, S1 as an alternate use, and you can use it either as one double precision register or two single precision registers, though not, of course, both at the same time. The FP registers have their own load and store operations, which work like the general purpose ones, but they load and store to and from the floating point FP registers. Now, our example program, quadratic.c, declares four doubles right up here, and it reads them, and then it computes the quadratic equation for on the assumption that A, B, and C are the coefficients of the equation, and then it inputs the result. Now, the compiler generated code for this is in quadratic.s over here on the left-hand side. It starts off by computing offsets for the three locals, A, B, and C, and passing them to scanf, much as the max computing program 5 did, and that's looking at right here on lines 19 through 23. But question one, there's an interesting difference from the earlier program. What are the addresses relative to FP of those variables, and what do you notice regarding their size? Well, the answer is the addresses minus 20, minus 28, minus 36. Those are 8-byte values. They're addressed at 8-byte intervals. Okay, so after the scanf, then those three variables, A, B, and C, will have values entered into them. Lines 24 through 41 do the quadratic computation, and they're almost entirely composed of floating point instructions, which is why all the opcodes begin with F. And they operate on the double precision registers, which is why they end with D, FLDD, FMLD, and so forth. Single precision instructions would end with S. The comments provided with the code indicate what the instructions do. FLDD, for instance, is a load instruction, and it is like LDR, but it loads to the FP registers instead of the standard CPU R registers. So lines 24 and 25 here load B into both D6 and D7. The FMLD on line 26 multiplies them to compute B times B, leaving that in D6. Lines 27 through 28 load A and the value 4.0 into D7 and D5 respectively, preparing to do a multiplication, but line 28 needs more explanation. First, there's an F copy D instruction that works like move, and it's used on line 33 down here to copy one register into another. But it does not permit assignment of constants, only other FP registers, so it's not as powerful as move. Thus, line 28 is forced instead to load the constant from memory, just as we would do for a constant too large to fit into a move instruction in the normal CPU assembly. The FLDD loads from L3, and it's of course a pseudo instruction. It's converted to a PC relative load. And since it's loading a double precision value, it loads two words, not just one, from location L3. So, consulting location L3, let's look down here. It looks like what we would do is load a word containing a 0, and then after that a rather complicated hexadecimal pattern there on line 54. But then that would imply all zeros for the first half of the number where the exponent is. It's at the start. It can't be right. So what's going on here? Now, this is the first time we've encountered what is usually termed endianness. When a value, for instance an integer, occupies multiple bytes in the memory, it's natural to assume that the bytes are placed in memory in left to right order, that we would naturally write them. If an integer, like for instance this large monster here, is say at address 100, then we assume that its bytes are placed in addresses as shown below it. Thus, with the most significant byte first, and then the next most, and the least significant byte last. Now, this is true for many CPUs, but some CPUs place the byte in the opposite order, with the least significant one first, like this, with the least significant 0111 byte first. These two storage approaches are respectively called big endian and little endian. I'll type that in here. This is big endian, and this one is little endian. The terms, by the way, are references from Swift's Gulliver's Travels, which is a political satire, not just a children's book. Gulliver at one point travels to a land where those who eat soft-boiled breakfast eggs from the little end first, the little endians, are at war with those who eat them from the big end first, the big endians. The reasons for the difference are not quite as silly as the Swift reference might suggest. When the CPU adds or subtracts multi-byte values, it does so from right to left, just as we would when adding least significant to most significant. And so little endian order positions bytes so that they're most naturally drawn from memory in the order needed for right to left mathematical operations. This assumes they're being accessed one byte at a time, though. That's not true in a modern 32-bit or 64-bit CPU, which draws values from memory multiple bytes at a time. But the earliest 8-bit microprocessors did fetch data one byte at a time back in the early 1970s, and it was a struggle to get all the needed circuitry for a single CPU onto one chip. So the little endian design was worth it to save circuitry and complexity. In particular, Intel used this standard in its early microprocessors. Once the little endian standard was set, all future Intel processors followed it for backward compatibility, and Intel is stuck with it to this day. Most non-Intel CPUs are big endian, and the ARM standard actually allows the user to choose which ordering to use. It's not obvious when you're dealing with a little endian CPU. It's irrelevant in registers, which are always in the expected left to right order. The LDR and SDR instructions silently adjust for endianness when going between register and memory, and any multi-byte constant that you provide in the assembly code is put into memory in the right order by the assembler. You only see the byte ordering when you deal with a multi-byte quantity in pieces, for instance loading individual bytes from an integer, or, as in our case, specifying two words for an 8-byte quantity. Returning then to lines 53 and 54 here, the words 0 and putting it in the hexadecimal form, OX401, all zeros. Those two words specify a little endian 8-byte double. The assembler will reverse order the bytes within those constants for us, but we have to put the two words in reversed order ourselves. In other words, the OX401 is the first half of the double, and the 0 here is, in fact, the second. So writing it out completely to save room, the double is in hex 0401 and all zeros. And so now that we got that sorted out, here's question 2. Convert that hex to binary form and explain why it represents 4.0 in IEEE floating point format. And the answer is, if you broke it apart into its three parts, sine, exponent, and mantissa, after converting to binary, this is what you get. Now that is a positive value with an exponent, that's 1025 less 1023, exponent of 2, thus, and a mantissa, of course, of 1.0, the 1 being automatically assumed before the binary point. So 1.0 times 2 to the second power is 4.0. So question 3. When a binary value is transmitted between machines on the internet, is it sent in little endian or big endian order? You can do a bit of online research to find this. It shouldn't take much. And the answer from your research should have shown that it's transmitted in big endian order, sort of the preferred order when there's a possibility of a choice. And then one more question regarding the line 28 that started this entire big digression up here. Question 4. We had to load the 4.0 because a fcopyd instruction can't move a floating point constant into a register. Why can't it do so? The answer is that any floating point constant, large or small, will take 64 bits. And that can't fit into a 32-bit machine instruction. Okay, moving along here. Lines 29 and 30, 31, 32, these are all fairly easy to follow. Please just read them and their comments. You're collectively accumulating a computation here, right? Line 33, however, is a little more interesting. It's preparing for the square root function call on line 34 here. And we know from prior examples that R0 holds the first parameter in a function call, but this works only for integer values. If the parameter is a double, then D0 holds that first parameter, since D0 has 64 bits and any operations on the parameter will use the floating point registers anyway. Similarly, D0 holds the resultant value, return value from the function call, as we can see here on line 35 after the square root call. Now, lines 36 through 39 are again unremarkable. Just read them and their comments so you can see what they do. Line 40 performs a division operation, as the comment indicates, and it's interesting because there is a division instruction for floating point, even though there is none for integers. Line 41 here stores the final result in X. Line 42 sets up the format string parameter in R0, but line 43 is not quite so obvious. An LDRD instruction loads from memory into general registers, but it loads 8 bytes into 2 successive general registers. The memory must start at an 8-byte divisible address, and the specified register must be even, with the implied second one being odd. For instance, LDRD of R2 from FP-12 actually loads X into R2 and R3. And the reason for that is that printf is declared as a variadic function, variable number of parameters, and the parameter types after the format string are unpredictable, so it doesn't follow the usual rule that doubles are passed in floating point registers. You will expect X in registers R2 and R3. And the remaining lines simply return a 0 from main and deconstruct the stack frame. Let's look at one final question here for this segment. Why is there a .align 3 on line 51? If you remember the rules for align 3 means to pad to an 8-byte boundary, 2 to the 3rd power. And the double stored at L3 needs to be on such a boundary per the requirements of LDRD stated above. Wants to have it at an 8-byte memory, 8-byte divisible memory address.